Hello again everyone, welcome back to ptet.chemistry channel. So my name is Dr. On, and in this tutorial video, I'll go through these 9701 Cambridge International A-level exams for the 16 to 18 years old chemistry curriculum. This is for a slightly older syllabus. This is June 15. Oops, I made a mistake. This is actually supposed to be November 15th, paper 21. So it was from the previous syllabus, so some of the questions within this particular exam paper might no longer be relevant, and I will point it out throughout this tutorial video that are no longer relevant or that have been adjusted slightly to mirror the changes in the new syllabus. Okay, so let's get started. In this first question, we have atomic structure kind of question. This is typical from O-level or IGCSE level chemistry as well. So filling in the table in terms of the relative masses as well as relative charges, we know that the actual charge of a proton is not +1, it's actually a very small number. We also know that the actual mass of protons, electrons, neutrons are not this kind of whole number, but they are actually a number with 10 to the power negative 20 something, 30 something for the electrons. So they are really small masses. These are simply the ratio of the masses and the ratio of the charges. The fact that this one has a zero charge, so only one out of the three particles are uncharged, that is going to be neutrons. Make sure you can spell them properly, Neutron. Neutron has the same mass as protons. They are the heavy masses concentrated in the nucleus of an atom. Together, neutrons and protons are what you call nucleons. And this thing, which has very small mass in comparison with the neutron and the protons, is around 2,000 times lighter. I never really remember this exact number. I always think about electrons being about 2,000 times lighter. Therefore, give or take around 1/2000. There's electron with a -1 charge and a proton with a +1 charge. Charges must have plus or negative unless when it's zero. So we're going to put in the plus and negative for these two particular species for that easy 3 marks to start off this question. Question 2, we have this relative atomic mass. The definition is in the syllabus. Of course, you're expected to know the definition of relative atomic mass together with relative isotopic, relative molecular, as well as relative formular mass. They are all stated in the syllabus for AS chemistry. For relative atomic mass is to do with the average mass of all the isotopes of the element, and then this is relative to 1/12 the mass of an atom of carbon-12. The fact that we are seeing this is element X mass spectrum, so on the x-axis we have mass over charge. Everything that passes through the mass spec will have a charge. If you don't have a charge, you won't see it, but this is from an element, so this element contains only one type of atoms, but there are 1, 2, 3, 4, and 5. So the fact that there are 5 lines means there are 5 isotopes of this element, and this element is element X. Some of them are present in a greater abundance, some of them are present in much smaller abundance. The fact that you have a lot of these isotopes with mass 80 means that your relative atomic mass is supposed to come down close to around 80 there. As expected, they do want you to define this particular term. For 3 marks, there are more lines for the relative atomic mass than the isotope. I would think the distribution of marks is supposed to be like 2 and 1. So Cambridge doesn't give out half marks. So you either get whole number or you get lesser than the whole number kind of marks. These are all stated in the syllabus as well. So relative atomic mass is defined as the average. So you must have the term average. It's not enough to just have keywords. This is average mass of all the isotopes. So an element can have more than one isotope, obviously, of the element. And this is in comparison, or this is relative to, or compared to the mass, compared to 1/12 times the mass of an atom, meaning one atom of carbon-12 isotope. So carbon-12 can be written as carbon-12. I prefer to write symbol where the 12 is on the top left because that's the mass number, that's the nuclear number, that's the meaning of carbon-12 there. Isotopes, they are referring to atoms of the same element. So they are different atoms, but they are for the same element. So what is different about their atomic structure? It's going to be same number of protons, so with the same number of protons, but different number of neutrons there. So the fact that you have different number of neutrons, so the number of protons plus the number of neutrons will give you the mass number or the nuclear number, and therefore you have different mass number and different nuclear number as a result of these. They don't mention about the number of electrons in here, but the fact that you are atoms, and if you have the same number of protons, your number of electrons must be the same as a result of atoms being uncharged overall. Now the next one is a calculation question. You're going to give your final answer to 2 decimal places and suggest the identity of x. Suggesting that you have to refer to periodic table for the relative atomic mass value that has this particular value that you're going to calculate out. So let's have a look at our table. So I'll probably set up my formula here and then just copy paste it onto the next page. So 0.89% times the mass 74. So the percentage abundance times the mass number, and then I have to add them up all together. So 9.37 times 76 plus 7.63 times 77 plus 23.77 times 78. I was wrong. There's not just 5 isotopes. 1, 2, 3, 4, 5, 6. There are 1, 2, 3, 4, 5, 6. I missed one just now because it has such a small percentage abundance there. But just to be careful about this kind of thing, running out of space there for my working, but no worries, I can easily move my things around. You can't on your actual paper when you'll be writing with ink, so you need to be careful and plan carefully. If you have to, you can write a second row as long as your working is clearly laid out, because that is what you can do as a student. And the sum of the percentages, these are percentage, sum of percentage is out of 100%, and make sure whatever you do, you use bracket very, very wisely. So I'm just going to copy paste that. So I'm going to cut that, and I'm just going to go to the next page and paste it here. So my working seems a bit long because of all that thing. Seems like only 2 marks. You could probably have just, press a calculator and you just write down the numerator and denominator. So 0.89 times 74 plus 9.37 times 76 plus 7.63 times 77 plus 23.77. Oh gosh, okay, I made a mistake with my calculator. So you gotta be very careful that you are keying in the right stuff. I better stop talking. As I'm talking, I might make a mistake again, and I don't want to waste time in a real exam. So I got 7904.21 divided by 100. I could roughly tell my answer is correct because my mass number is very close to 79 and very close to 80 and also 78, where I have a lot of 80 and a lot of 78. So it makes sense the average is give or take around that region. So 2 decimal place, so 79.04, 2 decimal place as required in the question. Oops, that should be the AR value. So straight onto your data booklet and have a look in your periodic table. So 79, look for the mass number. So 79.0, that looks to be element selenium. So selenium on my A-level periodic table has a relative atomic mass of 79.0, stated in the periodic table there. The next one, the element beryllium reacts with chlorine to form a single solid product, and this relative formula mass to 70. They use the term relative formula mass, but the actual calculation method is still the same thing as you would calculate MR. You just sum up the relative atomic mass. It's just that relative formula mass has a particular definition with respect to the ionic compounds that are forming between the metal and the non-metal. As you know, the metallic character, even though it's group 6, or group 16 as you would know in the new syllabus, the metallic character increases down the group. Now calculate the molecular formula of this chloride. To work out the molecular formula, we're given the relative formula mass, the MR, but we can probably work out the empirical formula first. If you have this much chlorine, so therefore the percentage of tellurium is going to be the remaining percentage, meaning the difference, because you only have 2 elements. You have beryllium as well as chlorine, so this is 47.4% beryllium. So I'm going to work out the empirical formula, simplest ratio of atoms, okay, simplest whole number ratio of atoms. So I'm going to work out the mole there. So in terms of the mole, there's the mass, 400 gram, tellurium in group 6, just below your selenium. So 47.4 divided by 127.6 mass over AR, because I'm talking about atoms, simplest whole number ratio of atoms. Similarly for the chlorine, 52.6 divided by 35.5 and not 71, because I'm talking about the atom, simplest whole number ratio of the atoms. So press enter calculator. So I get 0.371, and then the next one, well, obviously it's a lot of numbers. I'm not going to write all of them down. I'm just writing out a couple of decimal places. Now what I do is I want the simplest whole number ratio. So I have to divide by the smallest number. So 0.371 is the smallest number. And then 1.482 divided by 0.371. I get 3.99, and that is really close to 4. So what I can say is the empirical formula is going to be TeCl4. So what we know is the MR of the empirical formula times by a certain factor. This will give us the MR of molecular formula, something you will have done from your O-level as well as IGCSE there. So there's 270. I don't know what factor I need to multiply it by. Therefore, I have to find the MR of the empirical formula first. So tellurium is 127.6 plus 35.5 times by 4. I get 269.6, which is pretty much 270. So you can see that the factor is just 1. When you get a factor of 1, this is not molecular formula. It simply tells you that the actual number of atoms in one single molecule correspond to the empirical formula, the whole thing multiplied by 1. So what you have is TeCl4 empirical formula. The whole thing just have multiple of 1. So when you have the whole thing expanded, this is the actual number of atoms in one single molecule. That's the definition of molecular formula. Even year 9 O-level GCSE and IGCSE students would know that that is the definition of molecular formula, actual number of atoms in one single molecule. Next thing, this chloride, TeCl4, it melts at 224 degrees Celsius, reacts vigorously with water. Think about the bonding and structure and explain your reasoning. So the first bit, we're going to be thinking about things like just above beryllium, things like SCl4, which you don't really do, but what you do is you do group 14 or group 4 chloride, which you know about SiCl4 does react with water. I'm not saying silicon is above beryllium, but I'm saying that you know about period 3 chloride, and they give you SiO2 and HCl, balancing every single equation you write. This is what you call hydrolysis. So we also know that that reacts vigorously with water. You get a steamy white film. We also know that that is simple molecular. It's a liquid at room temperature and pressure. This one, even though it melts at 224 degrees Celsius, the fact that it does that and it does react with water, meaning to say it undergoes hydrolysis, and it doesn't just dissolve in water. It doesn't just dissolve in water, unlike your normal ionic compounds like sodium chloride. Salt just dissolves in water, right? So the type of bonding that we have here, the TeCl4 has simple covalent structure, or you can say simple molecular structure. They both mean the same thing, but I need to mention the bonding now. So I have covalent bond. So this is strong covalent bond between the beryllium as well as chlorine atoms. These are non-metal, well, they're considered as non-metal atoms, otherwise they wouldn't have formed covalent bonds between themselves like that, okay? And then explain your reasoning. So relatively low melting point, relatively low. I'm not saying it's very low, I'm not saying it's like negative. So it is still a solid at room temperature and pressure because you haven't melted at 25 degrees Celsius. Relatively low melting point suggests a simple structure, a simple covalent structure. Okay, because if you have a giant structure, could be giant metallic, but it cannot be giant metallic because it's a compound, could be giant ionic or giant covalent, it will have extremely high melting and boiling point. So what are we breaking here? We just break weak intermolecular forces between the molecule when we melt this simple covalent molecule. So intermolecular forces means between the molecule. Last but not least, I should really explain the other thing as well because this N reacts vigorously. So we can say TeCl4 hydrolyzes readily in water. It doesn't just dissolve in water, it hydrolyzes readily in water. So meaning to say TeCl, covalent bond, will break when you react with water. Okay, upon hydrolysis, we don't really have to specify the product, but there is a violent reaction as a result of the hydrolysis happening. Well, actually, we might have to, because they are asking for what happened when the TeCl4 reacts with water. I can draw inspiration from what I had done previously with the silicon tetrachloride, which is from group 14 chloride, which is your period 3 chemistry. Oops, not silicon, but then TeO2 perhaps, tellurium oxide, and what I get could be HCl, and 4 of that and 2 of that suggest. So it's not in your syllabus, but it is based on something that you might be able to get from your syllabus, just like that. Now the next thing, these are chlorides of the third period chemistry, period 3 elements. So as I mentioned, silicon tetrachloride there, melting point, it's got very low because it's simple covalent structure. Now describe what you would see during the reaction between sodium and chlorine. This is not silicon and chlorine, but this is between sodium and chlorine. This is sodium metal, and then you have chlorine non-metal. Okay, so what you would see, well, sodium metal is not white in color. It's kind of like kind of dull color, I guess. When you cut it fresh, it's not reacting on water, so there's no water in here. Chlorine has a color. It's kind of pale green gas, but sodium chloride is a white color solid. So it's a white solid at room temperature and pressure. So as that form, you will see a white solid. But what will happen to the color of the non-metal? Well, this color will disappear as the chlorine reacts. And the sodium is a piece of metal, so you would lose the color of the metal itself, which, when freshly cut, looks a bit grayish. So it will, I think they call it lustrous, but then the lustrous appearance of the alkaline metal will disappear as the sodium reacts. Okay, so as the sodium reacts, what we could say, the lustrous, I think that's the correct adjective, the lustrous shiny appearance from the freshly cut sodium will disappear. It will fade away, it will disappear as it reacts. Okay, also as the chlorine reacts, the chlorine exists as a Cl2 molecules, the pale green color, so it's a pale green gas. The pale green gas will fade in color. It gets lighter and lighter as it reacts. But last but not least, we also observe a white solid being formed. So this white solid is sodium chloride, but you do not see sodium chloride. You observe a white solid being formed, as it is a giant ionic lattice structure kind of solid. It has high melting point, and therefore it exists as a solid at room temperature and pressure there. Now in terms of the melting point, this comes down to structure and what bond do you need to break. And you should also refer to the difference between the electronegativity. We know that electronegativity is the ability of an atom, is the power of an atom to attract the bonding electrons towards itself. So looking at this 2.2 and 3.1, so this is a bigger difference in electronegativity. So when you have bigger electronegativity difference, it kind of shift more towards the ionic bond kind of spectrum, whereas when you have small electronegativity difference, so things like non-metal and non-metal, they prefer to form covalent bond. So in terms of the explanation, I can say that the smaller electronegativity difference, so they want us to refer to that, right? So I can say it's the smaller electronegativity difference between silicon and chlorine compared to. So you can have different way of explaining things. All I'm doing is I'm just outlining my thought processes here, okay? Compared to between sodium and chlorine means, so we are talking about the small electronegativity difference, means silicon and chlorine are more likely to form covalent bond. Whereas the bigger the difference in your electronegativity, something likes to lose, something likes to gain in terms of electrons, and therefore you would shift towards ionic. Okay, so in terms of the bigger difference, what else? You should refer to the difference. Okay, explain the difference in terms of their structure and bonding. So NaCl has giant ionic lattice structure, as you would know from your O-level stuff, your GCSE or your IGCSE knowledge as well. So we need to break. So melting NaCl needs to break very strong ionic bond or strong ionic bond, and this is between oppositely charged ions. So this is between Na plus and also Cl minus. In terms of the next one, the SiCl4 has a simple covalent structure or simple molecular structure, whichever one you prefer to use. So simple covalent structure or simple molecular structure is the same thing. We're talking about boiling. No, we're talking about melting point. So I guess I should think about melting as well. So melting SiCl4 only needs to break. So here is where your adjective is very, very important. This is your weak, and I have to specify my intermolecular forces, as that is something you have learned as London dispersion forces or van der Waals forces. London dispersion forces are the new terms they use in the new syllabus, but if you use van der Waals, it will be accepted as well. And these things are non-polar, as it is a tetrahedral molecule with a symmetrical distribution of charges, because all the atoms around this tetrahedral geometry with zero lone pair, the dipoles cancel out despite the bond being polar, but the dipoles cancel out in this particular geometry. And these are weak van der Waals forces. These are between the molecule. Between the molecules. Running out of space here, but let me just complete that. Between the molecules. In terms of the explanations for the electronegativity, I've only mentioned about the covalent bonds. I haven't mentioned anything about the ionic bonds, so I don't think I'll get the full marks yet. So when the electronegativity difference, when the metallic sodium and non-metallic chlorine has much bigger electronegativity difference, this will shift the bonding spectrum towards this shift the bonding spectrum towards being ionic. Then how in the world do we know whether it's ionic or covalent? You don't really. So bonding is a spectrum, like I said. So it's not like one specific value would tell everything. But in general, when you have a metal and a non-metal, in general, they prefer the ionic bond, and because towards the ionic bonding regime, and that is because the metal sodium prefers to lose electrons, so not very electronegative at all, whereas in this case your partner, which is the non-metal, which is the chlorine, it's much more electronegative than the metal. It prefers to gain the electrons, and because that is much more electronegative compared to the metal atom. Whereas when you have the silicon and the chlorine, they don't have much electronegativity difference, therefore they prefer to share electrons, so they just share electrons. For that, SiCl4, they share electrons instead, and therefore they form covalent bonds. I think that's probably enough already. So I mean, I've just tried to answer the question as best as I could. Structure and bonding, probably 1 mark and 1 mark. A lot more lines in here, probably the distribution of 2 marks here. That's why I don't think it's enough to just talk about the small electronegativity difference there. I should talk about why ionic, why covalent there in terms of the electronegativity difference. And there's something that are in the new syllabus as well, where they will provide you some electronegativity difference value. Where they'll provide you some electronegativity, and you probably have to do some calculations to work out the electronegativity difference and probably explain the bonding spectrum like that. So that's the end of this 20-mark inorganic chemistry question. So inorganic chemistry is about 1/3 of the whole AS chemistry. So you can expect these 20 marks to cover the whole of inorganic chemistry for this particular paper. In this question number 2, we have an ideal gas question. So I can imagine this being the start of the physical chemistry idea here. So the first part here, draw one line on the graph. And what do they expect us to do? The relationship should be for the same amount of an ideal gas. If we look at our graph, we have PV on the y-axis. So P times V there. We know that Boyle's law. So Boyle's law basically states that at constant temperature, pressure is inversely proportional to the volume of a gas. And this only happens at constant temperature. So a lot of students, in fact, they do physics, but they forgot that the relationship only holds true at constant temperature. You cannot just simply say that without the accompanying statement like that. Having said that, then PV is equal to constant. This is for an ideal gas. So we could see that for an ideal gas, PV equal to constant. That means it shouldn't change no matter how pressure changes, no matter how volume changes. PV is a constant. So by right, it should be just a straight line, a horizontal straight line, because PV equal to constant value. It doesn't change irrespective of the x-axis there. State and explained. So there's two parts to the question. The first part is stating, the second part is explaining. So there should be two bits to your answer. With reference to the graph, which of the temperature is the lowest temperature? We know that the assumption, the most important assumption of ideal gas is to do with negligible intermolecular forces. Negligible means minimal intermolecular forces. In terms of temperature, you want the temperature to be as high as possible so that the molecules are further apart, so that the particles are further apart, and then they exert very little intermolecular forces between them. When you have low temperature, your particles are closer together. So if your particles are closer together, your intermolecular forces will be stronger. If your intermolecular forces get stronger, we can imagine these being less ideal. And when they become less ideal, we can expect them to deviate the most between T1, T2, and T3. We can see that T1 deviates this much at this particular pressure, and then if I look at another one, T2 deviates around this much by the green color, and then T3 deviates by around this much. So in terms of the T1, T2, and T3, the greater the deviation, the less ideal it becomes. The lowest temperature means the particles will be closest together, intermolecular force would be the strongest, and therefore is the least ideal. The least ideal would be the red color one, because that is the that will be the one that deviate the most from the ideality assumption there. Okay, so T1 is going to be the lowest temperature based on what I have said. That is the one, the graph above. So you need to use the graph. The graph above shows the greatest deviation from ideality. The greatest deviation from ideality, consistent with, so I'm trying to explain now, consistent with stronger intermolecular forces. So I can't use IMF because there's abbreviation. So stronger intermolecular forces as a result of molecules being closer together, or particles being closer together. I don't want to use the word molecule because we are not sure about what this one is. And this one is at lower temperature. The particles are closer together, and as such, stronger intermolecular forces, greatest deviation from ideality, as I've just explained earlier. Now explain your answer in terms with reference to intermolecular forces. It seems that I have actually done the next bit in this bit here. That was a bit strange because there was only 1 mark there. I think I can then use the second bit of the explanation, the consistent with stronger intermolecular forces, for this second bit here. So let me just move my point around. So sometimes it's quite challenging, isn't it? Like you put your answer in one part and then you don't really have the chance to actually write in the next part again. So in terms of stating and explain the previous question, there was one, and there was just the greatest deviation from ideality, I guess, because then the next bit is talking about the intermolecular forces, and there's a result of the particles being closer together at lower temperature. Alright, so on to the next question. So what do they want now? They want to state and explain, so the first part and second part again, the effect of pressure on the extent to which a gas deviates from ideal behavior. So now this is on the effect of pressure. We can think about, like when you have a gas piston like that, and you have a certain particle like that, and then you allow the piston to move a little bit out, but your particles, you still have the same amount of particle inside. So as I allow the piston to be moved out, going from here to here, I can think about the pressure decreasing. So when the pressure decreases, we can see the volume occupied by the gas, which is the volume of the container, would actually increase going that way. And that is basically the Boyle's law, which is applicable at constant temperature. So we could imagine as the pressure, so using the graph, as the pressure increases, we can see that these are for a real gas at 3 different temperatures. Let's just look at the one where it's just one particular temperature. Let's just look at T3 for instance. So this is the one that deviates the least from the ideal gas. This must be the highest temperature. But even for the highest temperature, we can see that it still deviates from ideality, where PV equal to constant for an ideal gas. And that is because at low pressure, your particles are further apart and they exert minimal or negligible intermolecular forces. Therefore, they are more ideal at lower pressure. Whereas at higher pressure, you're squeezing the particles closer together by decreasing the volume in which they occupy the container in. And as they occupy a smaller volume, they get squeezed closer together, and therefore they will become less ideal as they exert greater degree of intermolecular force. And when they get less and less ideal, you can see this going further and further up as they deviate more and more away from ideality. This is in terms of the changes in pressure. So I can talk about as pressure increases, probably going to explain first in terms of the one of the other assumptions of ideal gas, which is to do with negligible volume, or they have zero volume considered relative to the container size. But as you increase the pressure, you're making the volume of the particle less and less negligible relative to the size of the container, the volume of the container. So as pressure increases, the particles become closer together, the particles occupy smaller volume of the container. They get squeezed closer together, they become closer together, and this is the bit where you talk about breaking the assumption. So therefore, they exert greater intermolecular forces or stronger intermolecular forces between the particles. And these are forces of attraction between the particles, and they become less and less negligible, and therefore they become less and less ideal. Therefore, less ideal at higher pressure. And as such, we could see a greater deviation from ideality as seen from the graph here. We see a greater deviation from the PV equal to constant ideality for an ideal gas then. So instead, I explained the effect of pressure on the extent, less ideal at higher pressure. So that was just a stating bit, and I've just explained it in terms of the negligible volume of the gas particle relative to the container being less negligible volume as a result of the particles being squeezed closer together. Also, that will result in a stronger intermolecular force as well. So basically, they become more ideal at low pressure and also at higher temperature there. Now we got a calculation question in this next part here. We have a flask filled with a volume of 100 cm cube. So that's going to be the volume of the container. So the volume of the container is going to be the same as the volume of the gas, because gas fills up the volume of the container. Now what do we have? We have another gas Y filling the flask, and we measure this at 26 degrees Celsius. Keep an eye out for this. When you have ideal gas equation, PV equal to nRT, PV equal to mass over mRRT, you want the MR there. The MR is going to be move up there and move the PV down there. You're going to get mRT because you keep the M, you keep the R, you keep the T. They got multiplied together and they get divided by PV, whereas 1 over MR, the MR move up there, PV move down there. This is the general expression here. We never memorize this. We think about this, and from this we can get this very easily. Now what is very important is the temperature must be in Kelvin, and this is 26 degrees Celsius, so you need to add 273 to convert that to Kelvin. This is in Pascal, which is alright, so pressure is in Pascal, or it could be Newton per meter square. The volume there must be in meter cube. The mass there must be in gram, because the unit of the MR is going to be gram per mole. So we have the mass of the flask containing the air, and we have the mass of the flask containing Y here. So what is going to be the mass of, let's see, we need to first work out the mass of the air first, I think, because the density of air is there. So what you're going to do is, you have density equal to mass over volume. So what is the mass of air? So mass of air is going to be density times volume. So 0.00118, that is gram per cm cube for the air, multiplied by the volume of the container, and you're going to get 0.118 gram. Okay, so that is the mass of the air. In terms of what happened next, you need to take away the mass of air from the mass of the flask, because this thing here, the mass of the flask containing Y, is going to contain the air as well. So what's going to happen is, no, cannot be. If you read the question, this is, first of all, you fill it with air, and then you fill it with another gas Y. So I need to find what is the mass of the flask first, because I know the mass of air already. I need to find the mass of flask. So the mass of flask is going to be the difference. The mass of flask is going to be number 1 minus this thing here. So it's going to be 47.9, what am I doing here? 930 minus 0.118 gram for the air. So what I get is 47.812 gram. Running out of space here. I wonder whether I can squeeze my working down. Part 3, so the mass of Y is going to be the difference between the mass of flask containing Y minus the mass of the empty flask there. So 47.989, that's the mass of the flask plus Y minus the mass of the empty flask, and this is going to give me 47.812, so 0.177 gram. So having done all that, I think we are ready to sub in a few things, and then we can get cracking with our calculation, which is PV equal to nRT kind of calculation. I guess the difficult bit is really working out the mass of the gas Y there. Okay, let me just change the color so that we are not easily confused at what we need to do from this point onward. Now what else do we have? We have the volume of the container, which is 100 cm cube. So a lot of students had problem converting cm cube to meter cube. I never really memorized the conversion factor, because I know I could do primary school mathematics, where 1 cm is 1 divided by 100 meter. So 1 cm is equal to 10 to the power minus 2 meter. And then I could cube both sides. So if I cube both sides, whatever I do on the left hand side, so 1 cm cube is equal to 10 to the power minus 2 meter cube. So therefore, 1 cm cube is going to be equal to 10 to the power minus 6 meter cube. So whatever is in cm cube, I just multiply by 10 to the minus 6. I could convert that to meter cube very, very easily. This thing plus 273 will convert that to Kelvin. This is already in Pascal. So I'm all set to just plug into the formula. MR equal to the mass. Mass of what? The mass of the gas in gram, because all of this belongs to the gases. Since this is an ideal gas equation, everything in here, mass of the gas, temperature of the gas, volume of the gas, pressure of the gas. So be very careful, it's for the gas because it's an ideal gas equation after all. R is at 0.31 joule per Kelvin per gram, and then the temperature is 26 plus 273. So should have done that on my calculator earlier. So there's 299 Kelvin. So I'm just going to multiply by 299 Kelvin, and then this is divided by PV. So the P is 1.00 times 10 to the 5 Pascal. And what do I have for the V is 100 cm cube. Converting cm cube to meter cube times 10 to the power minus 6. Now it's time to press your calculator after you have gotten everything set up properly. Divided by 100 and times 10 to the minus 6. So what I get is 43.979. They didn't ask us how many significant figure to give this one to. If you look at the data, this is 1, 2, 3, but this one has got a lot of significant figure, too many significant figures, but this one is also 3 significant figure. For the pressure, I would say 3 significant figure based on the data is appropriate. So I'm just going to run this up to 3 significant figure. This has a unit of gram per mole. If you don't like that gram per mole, you can use gram mole minus 1. I don't think they'll penalize you for the unit, but I guess, you know, it never hurts to actually know that the proper unit for MR is gram per mole there. So in this next part of the question, why is nitrogen very unreactive? We know this is down to the very strong nitrogen-nitrogen triple bond that needs to be broken down, and as such it has very high activation energy before the reaction could even get started. So this is very strong nitrogen-nitrogen triple bond, triple covalent bond. If you have these data of the bond strength, the bond energy from the data booklet, you should really quote the value. But I understand that in the latest newest syllabus that the data booklet is no longer provided in this paper 2 setting. Instead, what you have is you have a list of data that will be accompanied inside the question paper itself. That is per the 2022 A-level Cambridge International syllabus onwards. So very strong nitrogen-nitrogen triple covalent bonds need to be broken before they can react. That is the reason why the reaction will have very high activation energy and therefore very slow and very difficult to initiate. Now, as for the next question, why are the conditions inside a car engine then? Why is that suitable, or why would that result in the production of oxides of nitrogen? Based on what we have said earlier, you do need to break this nitrogen-nitrogen strong triple bond. So inside the car engine, so we are combusting, we are doing combustion of fuel. So this combustion of fossil fuels, well, I guess I don't want to generalize it with fossil fuels because you could be, you know, using a fuel cell or something, but essentially you are consuming fuels. So this combustion of fuels produce or release a large amount of heat energy, and this is sufficient to break the nitrogen-nitrogen triple covalent bond, allowing the N2 to react with oxygen in the air. So you have O2 that's present in the air in about 21%, and you already have 78% of nitrogen in a dry air to begin with. Now give an equation, meaning one equation, for how you're going to remove the nitrogen monoxide, so that is NO, from a car exhaust in the catalytic converter. So what the NO is going to do is it's going to react with CO, and these are dirty, basically pollutant and pollutant. And what we're going to do is we're going to form CO2. So the CO steals away the oxygen. Basically, the CO gain the oxygen from the NO, the CO get oxidized to form CO2, and then the NO loses the oxygen and you will get N2. Of course, we know better than to leave any equation unbalanced. Having done A-level, you should know that you can use fractions. If you really don't like to use the fractions, you can have the whole thing multiplied by 2. Then you get 2NO plus 2CO and 2CO2 plus N2. Just like that, you get a 1 mark down there. Okay. In this equation, you also have the use of a catalytic converter. So the typical catalysts like rhodium, palladium, platinum catalysts. Now these are transition metal as a solid as the metal itself. So these catalysts are in a different state as these gases in the catalytic converter, passing through the catalytic converter, and therefore this is going to be a heterogeneous. I was about to say homogeneous, but they are in a different phase or different state as the reactants there. So that's why they are called heterogeneous catalysts, and these are one of the few definitions inside the AS rate of reaction topic. Now the last bit of this whole question, one of the main reasons for reducing the amount of oxide of nitrogen is due to the fact that they can form acid rain. We know these are oxides of non-metal, including oxide of nitrogen, oxides of sulfur that can result in acid rain. We're going to form nitric acid. So you form nitric acid from NO2. this can be a difficult equation to write if you don't know what you're looking for. So what we have is NO2 dissolved in water, and you get HNO3, that is nitric acid. But whatever you try and do, you will not be able to balance the equation unless you know the other product. The other product is actually going to be HNO2. So in order to balance this equation, you really need to know that this is one of the classic disproportionation reactions. So you have learned a couple of classic, especially the one involving chlorine and NaOH. But this is one of the disproportionation reactions involved in the formation of acid rain directly from NO2. This is nitrogen plus 4 oxidation number. Since each of the oxygen is -2, you get 2 of the -2, so the nitrogen is +4, giving the overall oxidation state of the molecule, the compound having 0 oxidation number. When you have HNO3, what essentially you have is 0 for the overall molecule, 0 for the overall compound, +1 for the one hydrogen, and then the nitrogen is what you want to find. You have 3 oxygen, each of which is -2. The nitrogen there is going to be +5. So we have a nitrogen +5, and now you have HNO2, which you will learn as HONO, or HNO2 is basically the same as HONO. The name is called nitrous oxide. You will use this in A2 benzene chemistry. So what we have is 0 for the overall compound, and then you have +1 for the one hydrogen. Nitrogen is what you want to find, 2 oxygen, each oxygen of which has a oxidation number -2 in the compound there. So that's going to give you +4 - 1, that's +3. As you could see, changes in oxidation number, the +4 there going to +5 is an increase of 1, the +4 there going to +3 is a decrease of 1. Changes in oxidation number has to be balanced out. In this case, they are balanced out. This is a redox reaction. That's why I say if you don't know the other product, it's almost likely that you won't be able to balance this equation easily. There are 2 nitrogen here, so I need 2 nitrogen there, and what I have there is 2 times 2, 4 oxygen, plus 1 oxygen is 5 oxygen, and 2 hydrogen, 1 and 2 hydrogen, 3 and 2, 5 oxygen there. Now, speaking of which, this very last equation is another very important case study. This is about the catalytic role now of the NO. The NO is acting as a catalyst to oxidize the atmospheric SO2. We know SO2 can go to SO3 in industry. Those are man-made SO3. Those are man-made H2SO4 coming from the man-made SO3. But this is happening in the upper atmosphere. This is natural oxidation. So the NO plus the SO2 is another classic, not disproportionation, but this is a classic environmental chemistry equation that you need to know how to write. This will give you SO3 as well as, am I correct? Oh, yep, the SO2 steals away the, now that doesn't look right. No, that doesn't look right at all. It's actually supposed to be NO2. So what actually happened is the NO reacts with O2 first. So the NO reacts with O2, and that give me NO2. And having said that, I need to balance my equation. I can have half there, or I can have 2NO plus 1 O2, giving you 2NO2. I was playing around with the earlier equation because I was looking around for the oxygen, because I know it will form SO3. So that means the SO2 has to steal away the oxygen from the NO2. If I started from NO, then there's only one oxygen to be lost and I wouldn't be forming back the NO2. So I knew I was wrong. The SO2 has to steal away the oxygen. Now I have one extra oxygen. I become SO3. The NO2 loses one oxygen. That is reduction there. This is gaining oxygen. This is oxidation there. Now what happened then with the SO3? Well, they don't actually ask us for how the SO3 form acid rain. They just want us to oxidize the SO2 to SO3. But typically, when it's a 3-mark essay question, in terms of the equation, the SO3 can react with the rainwater, and you will get H2SO4. So this is going to be your acid rain, which is acidic, and this is going to be your rainwater, in which the SO3 which you just produced can dissolve in order to give you the acid rain. Of course, a few dangers of acid rain: to make river water acidic, they kill plants, they kill animals, and they can damage limestone building as well. So quite a huge amount of marks for this inorganic chemistry that we've done so far. Not just inorganic chemistry really. So we started from a little bit of physical, some ideal gas questions, some Boyle's law, but then you move on to environmental chemistry fairly quickly there. Question number 3, what we have here is organic chemistry reaction. So as you know, this is ethanol, and this is delta minus and delta plus. And what you're doing is you are adding the HCN onto the aldehyde, such that what you get is you get a what did you call this again? I forgot what you call this already. Cyanohydrine. So it's got an OH, it's got a CN on the same carbon. This is a result of nucleophilic addition mechanism. The mechanism is nucleophilic addition, but the type of reaction is basically addition reactions, as stated in the introductory organic chemistry bit. What do they want us to do? They want us to use some bond energy from the data booklet. So if this is in the present 2022 syllabus, the data booklet data itself will be in the question paper. So you need to know that you get the data from inside the question paper. Perhaps at the end of the question paper or at the beginning of the question paper, you would definitely have the data somewhere. Now calculate the enthalpy change for these reactions, include a sign with your answer. So if we think about it, we are not told that everything is gaseous state, but if we use bond energy, that's because the question asks us to use bond energy. So I'm just going to display the bond so that we can see exactly what is happening from left to right. So display formula means show all the covalent bond. Why do we do that? Because we want to see exactly what happened going from left to right. So that is essentially what happened there. So going from left to right, you can hopefully see that, what do we have? We are breaking the CO double bond, and then we are forming a CO single bond. Perhaps I should use a different color. And we are breaking this HC bond. So I'm going to use a green, no, green is not good, a blue color to represent the bond we are forming. We are forming that. And what else are we forming? We are forming the C and C covalent bonds. So we break that and we form the OH covalent bond, and we break the CH and we form a CC covalent bond there. Of course, this reaction is catalyzed by a small amount of NaCN, could be KCN, because that thing is a nucleophilic, a much more nucleophilic source, which is a full ion compared to this being a simple molecule. So I'm going to have a look at my data booklet, because this is still question from the old syllabus. Of course, the new syllabus, you will have the data like I said in the question paper itself. So the red one is what we need to break. In terms of bond energy, we know that the enthalpy change of reactions is the sum of bond energy broken, whatever you need to break, minus the sum of the bond energy that you need to form. So in terms of what you need to break, let's see, what do we need to break? We need to break a C double bond O. Gotta choose the right one. C double bond O. 740. So I break one of that. I break one of that C double bond O. I also need to break one of the CH covalent bond. So that is 410. So I use a bracket to close up the bond energy that I need to break, and then I take away the bond energy that I need to form. These are CO single bond, so there's 360, and there's 360 multiplied by 1, and then I have one of that carbon-carbon single bond, that is 350. And what do I have altogether? Just need to move that up a little bit, and let's just press that and key that into calculator. So my first addition give me 1150, and the second one give me 710. So 1150 minus 710. Of course, your calculus show you 440, but you know, include a sign. Even when they don't say include a sign, you know the enthalpy change has a sign, a value, as well as a unit. So always be aware of what you are calculating there. Now, the product of this reaction shows stereoisomerism. We know that stereoisomers refer to molecules having the same molecular formula. So they have the same molecular and also structural formula. That is why they are not called structural isomers. They are called stereoisomers. So they have the same molecular and structural formula. But what is different? They have different arrangement of atoms, all groups of atoms in space in 3 dimensions. So different arrangement of atoms or groups of atoms in 3 dimensions in space. Now, what about chiral center? So we know chiral center is a carbon atom which is bonded to 4 different groups or atoms. And they will give rise to enantiomers, which are the non-superimposable mirror images of each other. That is another definition you have to know. So these chiral carbons bonded to 4 different groups of atoms. 4 different atoms or groups of atoms. Okay, I think I've gotten them mixed up a little bit. So 4 different atoms, or it could be groups of atoms, and as a result you get enantiomers. Enantiomer is another word you need to know. Like I said, enantiomers are basically the pair of optical isomers. They are mirror images of each other, non-superimposable. Now why is it that the 2 optical isomers are produced in equal amount? That is actually what you call racemic mixture. You will learn more about this in organic synthesis as part of A2 chemistry. One of the popular questions they like to ask is something like that. Well, if you think about this reaction here, you do get a chiral center here on this carbon. Carbon form 4 bond, CH3, CNOH, and this is skeletal, so there's a hydrogen which is not shown there, which is there. And you started from this CO carbonyl, that is a carbon sp2 hybridized center. So it's a trigonal planar center there, and after that you get this thing which is tetrahedral. So if I think about the mechanism, so you have C double bond O there, so you have a hydrogen and then you have a CH3, so it's trigonal planar like that. And what happened then, that is the pi bond. The pi bond is a sideway overlap of orbitals like that. But what we can imagine is we need to break this pi bond obviously, but this thing is trigonal planar. So what it means is the nucleophile, the lone pair on the CN of the CN minus of the catalyst is the one that can kickstart the reaction. It can attack from the top or it can attack from the bottom. So what we can say is the starting aldehyde, the starting reactant aldehyde, RCHO. So the starting aldehyde has a trigonal planar carbon sp2 at the carbonyl carbon. So the C double bond O is the carbonyl carbon there. This allows the Cn minus nucleophile to attack with equal chances. So it's about the equal chances or equal opportunity that result in equal proportions of the resulting optical isomer, where you have one where the Cn minus will attack from the top and therefore it will be stuck on the carbon from the top, or the Cn minus attack from the bottom and the Cn, the carbon there, will be formed at the bottom face there. So they attack with equal chances. Onto the carbonyl, and therefore you get a racemic mixture. So even though you get an optical isomer, they are called optical isomer because they have optical activity. They will rotate plane polarized light, but because you get a racemic mixture where you have equal chances of the nucleophile attacking on these, and therefore you get equal amount of the enantiomers, the mirror images, so they will rotate plane polarized light in opposite directions, even though you have a chiral center, even though you will get optical isomers, but you have a racemic mixture where they rotate plane polarized light in opposite direction. Racemic is actually a word in optical isomerism topic in AS chemistry. Now, organic chemistry will almost not be complete without them asking you to draw mechanism, the usual nucleophilic addition mechanism, partial charges or full charges as well, because we're going to be talking about oxyanions. The lone pairs are important for the nucleophile. The curly arrows are important for your mechanism. So the first thing you start out from is this Cn minus. So it's got a negative charge there, but it's not the negative charge that actually attack. It's actually the lone pair on the carbon. So it's the lone pair on the carbon that will attack the carbonyl. So what we have there is a delta minus on the electronegative oxygen, leaving a delta plus on this carbon there. So what happened is the lone pair on the carbon with the Cn minus will attack the poor in electron, and then it will break the CO double bond. Having done that, what I have now is a carbon and then a Cn like that, because I don't break the C triple bond end. In fact, I form a C single bond C. I just break the C double bond O there, as you could see from the mechanism. So what I get then is O minus, because the 2 electrons go to the oxygen. Now the oxygen forms single covalent bond. It has a lone pair there. I must label my dipoles on the HCN polar molecule. It's not ionic, it's polar. Now what happened is the lone pair on the oxy anion attacks the poor in electrons, and now it breaks and gives the 2 electrons back to the carbon, and I will regenerate the Cn minus, and this thing has a lone pair of carbon again, and they can attack more of your aldehyde starting material until all the aldehyde has been used up, and you will kick out another Cn minus, and having done that, you will regenerate back the catalyst. So explain why the Cn minus is a catalyst, because at the end of everything, you will always get back one Cn minus. It's not the original Cn minus from the NaCN or KCN catalyst, but regardless, you still get Cn minus. Chemically, it's unchanged. Physically, it might have changed, but chemically, it's still the same. There's the property of it acting as a catalyst. Now, this thing is called an oxy-anion intermediate. So it's not your usual carbocation intermediate. This is one mechanism in which you have the negative charge on the oxygen there. Explain the role of the NaCN. So the NaCN is acting as a catalyst. So it acts as a catalyst, and it's just to speed up the reaction. So Cn minus is a much better nucleophile because it's fully charged compared to that polar molecule than HCN, which is a poor nucleophile. So it's only polar, it's got dipoles, but it's not fully charged. It's a much slower nucleophile, obviously not very good nucleophile, very slow reaction without the catalyst to kickstart the reaction there. Okay, so it acts as a catalyst, therefore NaCN will speed up the rate of reaction, will make the reaction faster, it will speed up the rate of reaction. I'm sure acting as a catalyst will be good enough. Anyway, so that's it really for this 12-mark organic question. In this next question, we have 4 alcohols. So they are structural isomers, so compounds with the same molecular formula but different structural formula. And these are C4H10O. So 4 carbon, they are 4 carbon alcohol. You should be able to draw or sketch for all of them, and we'll be able to do this with skeletal formula. That is the fastest and the most elegant way to do any sort of A-level organic chemistry. The alcohol A does not react with acidified potassium dichromate. We know that that is an oxidizing agent. So the fact that alcohol A does not react, this straight away tell you that A is tertiary alcohol, cannot be oxidized. So there's something that you have to consider from the very beginning. B, C, and D can be oxidized, so they are either primary or secondary alcohol. Now, all 4 alcohols react with hot concentrated sulfuric acid. In this context, what you're going to get is this C4H8. So this is an alkene. So we are not sure about what kind of form it is yet, but this thing is acting as a dehydrating agent. So what you could do is you could use hot concentrated H2SO4 because you need to remove the H2O in order to generate the alkene, getting you back the double bond, carbon-carbon double bond. So you would do this at around 200 or 300 degrees Celsius. You'll be passing out the water as steam. Now A, C, and D each give you a single product in this reaction. But what is important is you have B giving you a mixture of 2 structural isomers, one of which, so out of the 2 structural isomers, one of them shows stereoisomerism. When you have alkenes and stereoisomerism, based on the definition that we had in the earlier questions, stereoisomerism is broken down into the optical isomerism with a chiral carbon. That is less likely given that you have 4 carbon, but we'll check in a bit. But the other thing you have to consider when you have carbon-carbon double bond alkene chemistry, it could also be cis and trans, which is geometric isomerism. What is very important in this question, they bolded it for you, give the skeletal formula. In fact, I was going to do a skeletal anyway, because if you watch all my other topical playlists with organic chemistry, you know that I'm a big proponent, meaning to say I support students learning skeletal formula, because when you go to A2, there's no other way except for skeletal formula. Now, what I'm going to do first is I'm going to draw out I'm going to sketch out actually all the structural isomers, as well as probably even the stereoisomers for this C4H10O for carbon alcohol. C4H10O it's got a alcohol, so it's a 4 carbon alcohol. We knew that just now A is a tertiary alcohol, but what I'm going to do is I'm just going to draw straight chain first. 1, 2, 3, and 4. You will see that this is CH3, CH2, CH2, CH2OH. You will see that 4 carbons, 3, 4, 5, 6, 7, 8, 9, and 10, and 1 oxygen there. So straight chain alcohol there. This thing is what you call butane 1-ol. So this is butane 1-ol. Now that is definitely one of the isomer that we can have. What else can we have is we can have actually I'm gonna move around the OH first, so we can have butane 2-ol like that. 1, 2, 3, and 4. So this is a secondary alcohol now, because if you look at the carbon with the OH, the carbon with the OH now is bonded to 1 and 2 other carbons. It's a secondary alcohol. So 2 degree there refer to secondary alcohol. Butane 1-ol is a primary alcohol, because the carbon bonded to the OH is bonded to 1 other carbon. Now the next one which I can have, well, you might be thinking about this, you might be thinking about 1, 2, 3, 4, but you must also consider the lowest number for the important carbon, which in this case is the carbon with the OH. 2 is smaller than 3, and when you go that way, that is not different from this, because that is still butane 2-ol, so that is the same as that, so we don't consider that at all. But when I go back to the original 4 carbon here, butane 1-ol, we can see the 4 carbon straight chain here. We can branch out the straight chain. So what I could get is I could get still the straight chain like that, but now I have 3 carbons, 1, 2, and 3. Where can I put the extra CH3? Well, I can branch it out. So this is a branch chain. This is a straight chain. Between 1 and 3, the relationship is straight chain and branch chain. So this thing, they are what you call chain isomer. Whereas the relationship between 1 and 2, so butane 1-ol and butane 2-ol, as you could see from the name itself, this thing is what you call positioned isomer. The other one included under structural isomer as is what you call functional group isomer, but we're not going to do functional group isomer here, because we are told specifically that these are all alcohols to begin with. So what do we have here? This thing is got a chiral center. What else can I say? Straight chain, branch chain. Oh yep, I think I'm missing the tertiary alcohol. So this must be the tertiary alcohol. The carbons bonded to the OH is bonded to 1, 2, and 3 other carbons. So there are 4 carbons, 3 hydrogen, 3 hydrogen, 3 hydrogen. Carbon form 4 bond. You only show 1 bonded to the carbon. 1, 2, 3 hydrogen. Carbon form 4 bond. 1, 2, 3 hydrogen. Carbon form 4 bond. 1, 2, 3 hydrogen there, and another hydrogen there, so 10 hydrogen. This is your tertiary alcohol, which means this must be A, because A there was your tertiary alcohol that cannot be oxidized by this K2Cr2O7 H plus acidified that. So that is the skeletal formula for this tertiary alcohol. B is the one that when you dehydrate, when you remove the H2O, it's going to give you mixture of 2 structural isomer. The structural isomer in this C4H8 is the one that will show stereoisomerism. So they were not asking for stereoisomerism in the alcohol itself. Be very careful. What I'm going to do now is I am just going to remove the maybe not. I'm just going to move up the name so that I can make you see what's happening when I remove the hydrogen and the OH there. So when I remove that, what I get is just one product there. When I remove here, you can see that I can have this hydrogen removed from carbon 3. Then I could get this product, but then this is a trans isomer. I could also get cis isomer like that. And you could imagine that there is actually another one, so not a good color to choose. Let me choose this black color one. So if you see this black color carbon, you will see that there could be an alternative hydrogen on the other side. This is a CH3, this is a CH2. They are different hydrogen, which is why they will give you different product. So altogether, you get two structural isomers, but one of the structural isomer shows stereoisomerism, which is your cis and your trans. The cis, they're on the same side, the trans, they're on opposite side. How about this one? This one here, you can eliminate from there or there. It's just going to give you the same product because this CH3 is the same as that CH3, is the same as that CH3. They are symmetrical. They're going to give you one product like that. And how about this one? This one is also going to give you just one product because on the next carbon to the carbon with the OH, there's only one hydrogen. So it's just going to give you one alkene product like that. And that product is the same as that. Doesn't matter. This is the one where it was quite special. That must have been B because B is the secondary alcohol, is the one that gives you two structural isomers, one of which show you stereoisomerism, in this case the cis-trans geometric isomerism there. So B has to be the secondary alcohol, the butane 2-ol. If you look at this straight chain and this is branch chain, so this is very clearly what you call chain isomerism, straight chain versus branch chain there. What else can I say? Can I say anything about C and D? There's no other information given for C and D, so I guess I could put C, the straight chain, for instance. Doesn't matter which one you put as which one, I think, because you're gonna relate them in the end anyway. 1, 2, 3, and 4 like that. Perhaps can remove the number actually. 1, 2, 3, 4, and then the last one is going to be the straight chain, but then being branch. Well, that doesn't make quite much sense. Nope, that is wrong, I think. Is that wrong? 1, 2, 3, 4. That is butane 2-ol. What I want is this thing here, so I don't want that. I want this thing here, where the CH3 is at this position here. Then this is branch, because this one, the name is going to be 2-methyl propane 1-ol. Whereas previously we have 1, 2, 3, so we have 2-methyl, and this is propane because 3 carbon longest chain. This is propane 2-ol. So these and these, they are what you call position isomer, as you could see the 2 and 1 there. And these and these, they are what you call position isomer because this is a position 1, 1, 2, 3, 4. But this is 1, 2, 3, 4. This is butane 2-ol. Whereas this one is butane 1-ol. So what we get really is these are related together. These are your position isomerism there. What else? Straight chain, branch chain. So again, that is your chain isomerism. We don't talk about functional group isomerism here because they are all alcohols. So it's not like they are gonna have other functional group other than alcohol. So we don't talk about functional group isomerism, which actually comes under structural isomerism. So typically you talk about structural isomerism and functional group isomerism specifically when you have aldehydes and ketones. So those two are put together as a topic. So aldehyde versus ketones, they are functional group isomers. And then you have another one, which is carboxylic acid and also esters. So those are functional group isomers as well when you have the same number of carbon. Anyway, is that the end of the question? Not really. There was just 7 marks. We also have this next page there. So give the names. They want the names of the 2 structural isomer produced by the reaction of B with the hot concentrated sulfuric acid. So the 2 structural isomers are these, not these and these, but these and these. So this is 1, 2, 3, 4. So this is what you call but 1-in for the black color one on the far right. But 1-in, the lowest number for the alkene. And then both of these, they are called but 2-in. This is cis but 2-in. This is trans but 2-in. So give the names for both of them. So the other one is but 2-in. I think there is a space there, so I'm supposed to fill the space there. Now state which of these isomers show stereoisomerism and then explain why. Okay, so it's going to be this isomer, which is but2-ene. So I already identified that, so that is just the first bit. Now explain why do they show this particular stereoisomerism, cis and trans there. So the presence of the double bond, the presence of the carbon-carbon double bond that prevent or they restrict rotations, that prevent or they restrict free rotations about that carbon. Okay, so meaning to say you cannot rotate from this to the other one freely about this carbon-carbon double bond, the pi bond there. And we also have different groups, the second conditions. So and there are different groups. The second condition is something that a lot of students always miss out because they thought just because you have double bonds, you will have cis and trans. Not really. You must also satisfy the second condition. You must have different groups. Well, not really different group. You must have, you must not have the same group on the same carbon of the carbon-carbon double bond. In this case, for instance, this one, you have two groups that are the same on the same carbon of the carbon-carbon double bond, so you don't get cis and trans there. But here, the groups are on the different carbon, so you get different groups on the different carbon. I think the different carbon of the carbon-carbon double bond is really, really important because there's a second condition for you to get the cis and trans isomerism there. Last but not least, I think that's the end of the paper and the question actually. Draw display formula. Display means show all the bonds. So do not forget that you need to show all the bonds for display formula for these two stereoisomers. So remember it was but1-ene as well as but2-ene earlier. So I'm just going to show but1-ene first. So carbon-carbon double bond and then like that. And then put in all the hydrogen. So C4H8. Carbon form 4 covalent bonds. Carbon form 4 covalent bonds, so make sure you count carefully. 1, 2, 3, 4, so only 2 hydrogen there. Carbon form 4 covalent bond, 1, 2, 3, 4, so there's only 1 hydrogen there. Carbon form 4 covalent bond, I'm still missing 1 hydrogen there, so be very careful. So count all together, 1, 2, 3, 4, 5, 6, 7, 8, C4H8. Now I have a nope, I have done a mistake. This is not the cis and trans because this is stereoisomerism. I don't know why I did that. We have to draw the cis and trans actually. So not but1-ene, but but2-ene. So you got to draw the cis and the trans. So let's go back and backtrack on what I said. So that is like that. And we have a cis, so there's CH3. And they are on the same side of the carbon-carbon double bond. And this one has to have the hydrogen there. You can also count 4 carbon, 3 hydrogen, 6 hydrogen, 7 and 8 hydrogen. I'm going to do the same thing on the other side, but I have to have the CH3 on the opposite side now for me to show the trans isomer. They don't specify that it has to be cis here. You can draw the trans here and the cis here. As long as you show all the covalent bonds, you will be fine, and not to make the mistake that I made earlier and drew but1-ene, because but1-ene doesn't have the stereoisomer. It's the but2-ene that shows the geometric, which is the cis trans isomers as stated in the AS syllabus. Okay, that's it really for this 13-mark question. And I think that's it really for this whole paper. So thank you for watching, and I hope that silver membership will have been worth it, because there will be more and more tutorials added in the future as well on a weekly basis. And it's for a cup of coffee to support my work. And if those are useful, don't forget to check out the topical playlists. They are available for free as well, so do share the channel, do share the playlist, the master playlist link with all your friends, relatives, juniors, seniors in schools, etc., and hopefully it will help other people as well. Thank you for watching. I'll see you in the next tutorial video. Don't forget to click the button on the bottom right before you leave, like the video, share the video, or in general just spread the words about the channel, and follow me at ptet.chemistry on Facebook, Instagram, Twitter and Telegram to get connected. Thank you for watching again.